Welcome back to Sheet Metal is Fun. I'm Ken. This is Cujo. Today we're going to talk about the difference between sawing and shearing. It's going to be a good one today. You're going to be glad you stopped by. Cujo, what do you think, buddy? What about that face? Let's go talk about sawing and shearing. I'll see you guys inside. Sheet metal is fast. Sheet metal can fly. And last, but definitely not least, welcome back to Sheet Metal is Fun. Today we're going to go over sawing and shearing and the difference between the two. I want to first start, let's go back to one of our prior lessons, take a real short look at fractions, and we're just going to use that as a visual aid for when we get ready to talk about sawing. Last time we talked about fractions, we had the numerator and the denominator. The bottom number is always the whole. Today I'm in the mood for pizza. This is going to be our pizza right here. So this number on the bottom, the denominator, is always our pizza. The number on the top, how many pieces of that pizza do we have? So what we have here, we've decided to cut our pizza into two pieces. And then we've decided to give ourselves one of those pieces. Let's take that question mark out, put in a 1. So we have, there are two slices. This is always the entire pizza right here. All this number tells us is how many slices we've cut the pizza into. This number could be anything. This number could be 16. Now we've cut the pizza into 16 pieces and we only have one. So we have a lot less pizza. Before we had half the pizza. Now we have 1/16 of the pizza. You see, when this number is changed to 15, the pizza is still cut into 16 pieces, but we have 15 of those pizzas. So what I want you to do is vision, here's our pizza. Today's lesson is about the difference between sawing and shearing. If we had a pizza and we were going to cut it into 16 pieces, let's use a chainsaw. Everybody cuts their pizza with a chainsaw. Let's cut our pizza with a chainsaw. We're going to cut this pizza into 16 pieces with a chainsaw. There's going to be pepperoni, there's going to be cheese, there's going to be sauce, there's going to be bread. There's going to be a lot less pizza left over because we cut it, we sawed the pizza into pieces with a chainsaw. Now everything tastes like oil and two-stroke. So what we wanted to do was we don't want to saw the pizza, we want to shear the pizza. Now the difference between sawing and shearing is anytime you saw something, there's always what they call the kerf. The kerf always gives you a loss of length. So if I had a table saw and I had a 10-foot long board, I had a table saw and I set the backstop at 1 foot. My board is 10 foot long. I've set the backstop at 1 foot. A table saw is just a table with a saw in it. What a creative name. So we've taken our table saw, because we're talking about sawing, and we set the backstop at 1 foot. If we run that board through there, we are not going to end up with 10 1-footers out of a 10-foot long board, because every time we saw, we lose this kerf, and the kerf is loss of length. So how do we know that we're losing length? At the end of the project, there's going to be sawdust under the saw. That sawdust on the floor is what we lost from our board. So if we had a board and we cut it and we cut it and we cut it, every time we cut this board, our board gets shorter. That's probably the #1 difference between sawing and shearing, is because every time we cut this, we actually lose the width of the saw blade. So however wide that saw blade is, that's why whenever we're using the pizza example, just to make it more memorable, we used a chainsaw to cut our pizza, because everybody's seen how wide a chainsaw is. Imagine every time you cut that pizza with a chainsaw, there's less pizza. So if we cut our pizza into 16 pieces with a chainsaw, and we weighed it before and after the cutting, the sawing, it would weigh less after it was sawed into 16 pieces. Where if we cut it with a knife, as they do, or sheared it, we can take those 16 pieces and we have no loss of material. So if we took a pizza, sawed it into 16 pieces, and weighed it, it would be lighter. If we sheared that same pizza into 16 pieces, weighed it, the whole pizza and the sliced pizza, they both weigh the same. So if we started with a board, every time we cut, we lose length. We're losing length because the kerf is taking its price for doing us the favor of making that cut. So what we do with sheet metal is we don't saw sheet metal very often. It's rare if we do. What we do is we shear sheet metal. The one thing that's misunderstood about shearing is when you shear metal, shearing is actually taking the sheet metal to its breaking place. We're actually going to stretch the metal to the point where it actually breaks. So if we were to watch the process of shearing metal, it would look almost like stretching taffy. So if we were to take a piece of sheet metal and shear it, there's actually going to be a good side and a bad side. Let me see if I can make that drawing for you. So anytime we shear and we have a blade traveling down, and we have another blade traveling up, there's always a small gap. These two blades don't want to run into each other. They're always offset by a small amount. That small amount of gap, as the metal comes through here and is sheared, it is actually stretched until its point of failure. And so this piece of metal right here on the top, I'm gonna try to make the drawing bigger. Let's see. I'm gonna show you what that piece is gonna look like. The top blade came down and stretched actually it takes it all the way to a sharp point. Sometimes we'll call it a hawk bill. So the top piece is going to have a hawk bill down. The bottom one gonna have a hawk bill up, because we actually didn't saw the metal, we sheared the metal. So whenever we shear metal, we're stretching it to its point of failure, and it cannot resist the power of the shear anymore. And so it quits resisting and it gives up. And that's what we have whenever we shear something. Shearing is actually stretching it to its point of failure. And because we're stretching it to its point of failure, we're always going to have one side that's going to be sharp and one side that's going to be rounded. If we could look at the metal from the side. So a lot of times, depending on what we're doing with our project, that will decide which way we shear the piece off, because we always want the customer to come in contact with the rounded area, not the hawk bill area. So I think that is going to do the reason that there's, and I just want to touch on one more thing. The reason there's a little space here, we have to have room for the metal to stretch into this gap. And so along with that comes the understanding that we cannot put a 1-inch peg in a 1-inch hole. A 1-inch peg will not fit in a 1-inch hole. There has to be clearance. Either the peg has to be smaller or the hole has to be larger. So you can't put a 1-inch peg in a 1-inch hole. I think with that, I hope that you've learned a little bit about the difference between sawing. Every time we saw, the blade takes its share, and its share is known as the kerf. The kerf ends up with a loss of length. So if we had a board that was 10 foot long, we're not going to get 10 1-foot long. We're going to get 9 1-footers, and then this last one's going to be short, because every time we cut it, we took a kerf, and that caused a loss of length. So we're not going to get 10 1-footers out of a 10-foot long board. If this was a 10-foot long, our metal sheets come in 10 foot long by 4 foot wide. I can set the backstop on the shear at 1 foot exactly, and we can get 10 1-foot pieces out of a 10-foot long piece, because whenever we're shearing, there's no kerf, there's no loss of length whenever you shear. We're actually stretching it to its point of failure, and then it breaks off like stretching taffy. That's a good way to start. Let's head over to the bench and take a look at a few tools, and we're going to learn how some of these tools work and why they work. I'll see you over there in a minute. All right, welcome back. Today's lesson is about sawing and shearing, the difference between the two. Really, with what we're going to spend most of our time doing, we're not going to do much sawing. We're going to do shearing. So if sawing comes up later on, then it does. But today's lesson is going to be about shearing. And like I said, whenever you shear, you're actually stretching the metal to its point of failure, where it can no longer resist the shearing movement. And so come on in, I want you to see something. Next time you go to a hardware store, I want you to pick up a flat washer. I like the big ones because they're easier to hold and you get a better visual aid. This is a great example of what shearing is. If you pick up a washer and run your thumb gently over the edge, one side will be smooth. This is that hawkbill we talked about. The other side, there's that hawkbill. Because washers are punched, and punching is the same as shearing. Punching is just shearing in a circular pattern. So you're always going to have, this is a good visual aid. Next time you're at a hardware store, pick up a flat washer, run your thumb across there, and I just want you to be able to see the difference between the smooth side and the sharp side. so that every time we use a flat washer in construction, when you put your bolt through, it always goes through this way. Then you expose the round edge to the consumer. You would never put a washer in upside down, but maybe you didn't know the difference up until now. Now that you do, feel it. Every time you put a washer on a bolt, I want you to make sure that you've given that washer a little feel to make sure, is that the downside or the upside? So pick up a washer, give it a feel at the local hardware store. So with that, showing you that washers are punched, this is a number 8 Whitney punch. It punches a 1/4 inch hole through a 1/4 inch of steel. But what I've got today is some 1/8 inch aluminum. Come on in, I just wanted to show you. Let me see, can you get around this side? What I'm gonna do is I'm just gonna show you. You can see the movement right here. There's the punch coming down. And just like we talked earlier, you cannot put a 1 inch peg in a 1 inch hole. If we look here, the punch is a slightly smaller diameter than the die. The punch has to have room around there for the metal to be stretched to its point of failure. So if this was a 1/4 inch die and a 1/4 inch punch, this would come to a dead stop as soon as they met each other. But what happens is they make the die a little larger. So what we're going to do, I'm just going to show you. So since this is the top, we talked about the smooth side and the sharp side with the hawkbill. All I want to do is show you, if I feel the top side, it's nice and rounded because the metal was pulled into the hole. And that act of pulling and stretching it down inside the hole gave this a really nice finish. But on the opposite side, if you can get in there really close, let me see here. This is the hawkbill. This is the sharp side. And so let's look at the plug that came out. Look, if you can see that plug, it has a smooth side and it has a sharp side. You always have that on shearing, and that's the way shearing is performed. So what we do whenever we're shearing is we're focusing the energy to a very pinpoint location. So if you look at my snips, I'm open right here. Look the way the snips close. There's only one place, there's continually only one place where the cutting is taking place. Let me turn it this way. I'm going to do that one more time. All right, we ready? So what I want to show you is the differences. The shear blades don't come together this way. The shear blades come together this way, so that as we shear, we're continually focusing our power on a very small place. And the reason we focus that on a very small place is because that gives us leverage over the work. So as an example, let's just say we look into our toolbox, pull out our microscope. No. Magnifying glass. You'll figure out how to cut that out, won't you? No? All right, don't worry about it. So what we have here is a magnifying glass. This magnifying glass, if we were outside in the sun, would take the amount of energy collected through the lens, and it would pinpoint focus that energy. And with that, the amount of sunlight that comes through the lens isn't dangerous. But whenever we focus it to a pinpoint, now we have a lot of energy in a really small place. That's how you can start a fire, and that's how you can start a leaf on fire. You could write your name. but I wanted to use the magnifying glass so you understood the principle of focus. We're going to take the amount of energy that's in the lens and we're going to focus it down to a needle point. And so that's the same thing we're going to do with shearing. We're going to take the energy that we're producing with our grip and we're going to place it to the tightest place that we can. So you'll notice our snips are only coming together in one place. It's always just one place. And that's the same way if we look at our shear right here. If you look at the shear blade, it's almost touching here. See the gap? There's a very small gap. And the farther we go this side, the higher the gap gets. It gets so high that from this perspective, it's difficult to see the actual blade. And there again, we're going back to on the stomp shear, we have a stationary blade on the bottom and we have the moving blade on the top. And so the blade comes down at an angle. So there's always a focus of energy at the point of shearing, because remember, when we're shearing, we're stretching the metal to its point of failure. We got to stretch it to the point that it gives up and allows us to complete the shear. So one of the things I want you to see is, talking about energy, this snip has no compound action. So whatever energy I apply to this end is applied to this end. Although if you look from the pivot point to where I'm applying energy, this distance is greater than that distance. The reason they do that is to give us the mechanical leverage we need. So whenever we're operating a pair of snips like this, I want you to go back to the playground and I want you to see a teeter-totter. Now, what we have here is the distance between the end of the handle and the pivot point, that's the fulcrum, is greater than the amount off of the front. So as we apply pressure, we are going to increase our leverage because we've moved the fulcrum closer to this end. So the trade-off is we need a lot more movement on this end to accomplish the same amount of movement on that side. But that is where the leverage comes in. So we have a lot of movement and we have a smaller amount of reaction or action. And we've done that just by moving the fulcrum, which gave us a longer lever, which gave us more leverage to perform the shearing action. That right there, that's what's happening. Here's our fulcrum. Our handle is longer than the blades. So what we can do, the next thing up from there is our rights and lefts. These are the snips that you're going to use so often. And these are actually called aviation snips. And because they were widely used in the aviation industry at the turn of the last century. So what we have here, this is called a compound action snip. So we're going back to the fulcrum and lever again, the teeter-totter. And what this does, as we close the handle, we're going through a compound action because we're not pivoting like we are with the straight snips. We have 1 point of pivot on the big snips. We have 2 here, we have 1 here, and we have 1 here. So actually what we're doing here is we're giving the operator, more leverage to perform the shearing function. So what we're doing with here, we had a long handle and a short blade. What this one does, moves this thing even closer. So the downside is there's a lot more movement required, but the upside is with the additional movement, we gain additional leverage over the work. The work is the metal. So this additional leverage allows us to do more work. As the metals get thicker, they get a little harder to cut. One of the things that we have to be aware of is that whenever we're cutting, whenever we're shearing, we always want to be mindful of which of these two pieces are we going to keep. Which one is our work and which one is the drop. And so as we're performing the cutting function, look what I'm doing with my left hand. See how I'm rolling this up? Because this is the part I'm going to drop. This is the part that's going to go away. Now, anytime we're cutting, we're actually performing two functions. One, we're shearing the metal. We're performing the shear. There we go. The second and less commonly known action is we have to move the drop out of the way so that we can move the snip forward. And so if I was just going to make a loose guess, I would say 85% of your energy on a shear is to perform the shearing function. The other roughly 15% is actually to spread the metal apart to allow you to continue that shearing function. So what I want you to do is anytime we're shearing, rather than let one hand do all the work of shearing and spreading, because we have to spread the metal to pass our snips through. What I want you to do is take your unused hand, whether it's your left or your right, and use that hand to do the spreading function. And what that does is that gives you a little more strength, a little more leverage over the shearing motion, and it also gives your grip a little bit of a rest. So rather than use 100% of one hand and 0 of another, let's use 85 here and 15. And then eventually you may get to the point where you can cut for a little while in the morning with your right hand, and then you may get to where in the afternoon you cut with your left hand. And that way you give yourself a little more longevity, and you won't be so exhausted on one side of your body at the end of the day. Compound snips. There's no compound here. What we have is leverage because the fulcrum is closer to the shearing action. This one, they've doubled that. There are 2 pivot points, 2 fulcrums. And so it requires a lot more movement on the closing end, but that additional movement gives you more strength on the shearing end. So whenever you're shearing, whenever you're cutting, use your unused hand to perform the spreading function. I would say it's roughly 15%. So at the end of the day, that comes in handy. One of the things that I want you to always remember is while you're cutting, always hold the snip perpendicular to the work. What we want to do is I want to cut perpendicular. So see, with my left hand, I'm spreading. With the right hand, I'm shearing, spreading and shearing. What I want to do is always hold the snip perpendicular to the work. If I find myself cutting at a different angle, you're going to find your snip will make it very difficult on you. What it wants to do is it wants to roll up an edge. So let me just give you an idea. Let's say we have a piece of metal. What I'm going to do is I'm just going to look at this metal on the end. So we've exaggerated it for clarity. The shortest distance between 2 places is always a straight line. So if I wanted to shear this into 2 pieces, if I'm holding my snips perpendicular to the work, I'm going to be cutting in the shortest possible distance. That transfers into less strength required to complete the cut. If my snips are laid over one way or the other, now I'm cutting through at this angle. So I'm taking a distance and adding more distance. So now instead of making a cut through a piece of metal that thick, I'm cutting through a piece of metal that thick. So I've just added more energy requirement, and you're gonna, if you want to try it out, you're gonna see that your snips will not appreciate your creativity if you hold it at an angle. Either way, whichever way you want to hold it, always hold the snip perpendicular to the work, and you're going to make the shortest possible cut through the metal. We don't want to cut at an angle. That's just going to make more work, and honestly, in the end, it never works good. So, another thing I wanted to go over with, we always want to give ourselves the best chance of going home at the end of the day in awesome shape. So one thing I want to point out with a hammer, I would never put the nail here, put the hammer, and then try to push that nail through the board. So what we're going to do is we're going to use the inertia by the moving hammer, and we're going to let that inertia drive the nail in. So now, one thing that you're going to want to do is during your day, learn how to use a hammer. As you strike the nail, you don't have to hold the hammer down and prevent the bounce. Did you hear that? It's always going to want to bounce. The best and most efficient way that you can swing a hammer is work on your timing. Because imagine this. You hit the nail, move the nail into the wood, and as the hammer is bouncing off of the nail, as it will, if you work on your timing, now you're actually using that return energy to propel the hammer back and ready it for the next strike. So this doesn't look like that big a deal, but at the end of the day, if you're going to swing a hammer at nails or sheet metal, the next time we come around, our next lesson, we're going to make a plenum. And whenever we make a plenum, we're going to see what it's like to hit sheet metal a lot of times. And what I want you to do, I want you to remember, every time the hammer comes down, catch it on that bounce and work on your reflexes, and then allow that bounce to help you bring the hammer back and get ready for the next strike. What I want you to do, one of the things I want you to do, we've talked about this before. Everything that we're going to do here, I want you to understand why you do it. I don't want to just tell you to do it. There are people who work, let's say a mechanic, and they can work at a dealership. They do brakes, they do paint touch-up. They have one area of the vehicle that they work on. And so often, they're not familiar with the other components of the vehicle, so they don't know how the whole package goes together. What I want you to do is I want you to ask questions. You can ask here, or you can Google it. You can ask somebody else that you trust that knows. I want you to always understand, why do you do it? If you know why you do it, and not only why do we do it, how does what we're doing affect the rest of the project? So there are people that work on, let's say, airplanes. They come to work in the morning and they're given a notebook, change that left main tire on this airplane. And that's what, they don't ask you any questions. They change that left tire because that's what they do. But if you came to that person and asked them about any other part of the airplane, they don't know. What I want you to do is I want you to get to the point where you're curious about how does this all go together? How does one thing relate to another thing? So if I could make an example, let's say you start a new job tomorrow. Right next to the time cards, there's a big red button on the wall. It's big, it's that big. Somebody tells you, all right, you're the new guy. Every day at 3 o'clock, I want you to hold this red button down for 3 minutes at 3 o'clock. And you ask, what does this button do? And they tell you, you don't need to know. Just push the button. Just do what I'm telling you to do. Just do it. You don't need to know why you're doing it. I just want you to do it. So the first day, it's 3 o'clock. Oh, I gotta hold that button down for 3 minutes at 3 o'clock. The next day, I've got to hold that button down for 3 minutes at 3 o'clock. Maybe you only hold it 2.5 minutes. Maybe you hold it 2 minutes. The next day, it's 1.5 minutes. The next day, you forget. And then you realize, wow, I forgot, and nothing happened. I don't even know why am I pushing this button. I don't even know what's going on. Why am I even doing this? You know what? I'm not going to do it. So you go 2 weeks and you're not pushing the button and nothing's happening. And you look out in the parking lot and the craziest thing you've ever seen in your life, there's a dead shark on the forklift and they're loading this shark into the back of a van. You go, golly, what's the deal with the shark? And they say, you know what? That was the boss's shark. He raised that shark from a pup. He raised that shark his entire life. And every day at 3 o'clock, when you hold that button down, what you're doing is the shark tank is on the other side of the wall and you're feeding that shark. So we still haven't figured out why the shark died, but good for you that every day at 3 o'clock, you've been pushing down that button and holding it and feeding the shark. What I want you to do is if I would have told you on the first day, hey, here's part of your job. Every day, I want you to come over and push this red button, hold it down for 3 minutes at 3 o'clock. What you're doing is you're feeding the boss's shark. I guarantee you, you would never forget to feed that shark. So I don't know if that's a good example. It just came to me in a vision that I just had a minute ago. So we're going to cut it off there today. I hope you've learned something about shearing, about sawing, and maybe something about sharks. But I want you to always ask questions. Why do I do this? How does what I'm doing relate to anything else in this company, anything else on this project? So that's it for the day. Thanks for coming on by. Sheet metal is fun. Look at that tool tray. Rivet box. I've already had some of my snacks, some of my sweet. So that's it for today. I'll see you guys on the next time right here on Sheet Metal is Fun. Thanks for coming by. I sure appreciate it. See you later.